So it's my pleasure to introduce the talk by Suheil Khoury from American University of Sharjah, from the United Arab Emirates. And, well, he will speak about fixed point theory and Green's functions for the solution of differential equations. So please, Suheil.
Thank you so much for the introduction. Before I start my talk, I would like to take this opportunity to thank Professor Alexey Karapetyants and Vladislav Kravchenko for their organizing and coordinating this very successful seminar. And I don't want to forget to thank Tatiana and Riva. She always helps us with any issues with the Wi-Fi and so on. So thank her for managing and overseeing the online seminar. Honestly, the seminar, I like it so much because it's remarkably successful, and I think I attribute this one to its commitment to sustainability. Whenever a seminar is sustained, it's successful, and that goes to the organizer of the seminar. I like the wide audience, and diverse of the seminar, wide and diverse audience. Okay, so let me get started about this one. This is the title, Fixed Point Theory and Green's Function for the Solution of Differential Equations and Iterative Strategy. Okay, I will tell you about this title in a little bit, but just when I was introduced that that I am a faculty member at the American University of Sharjah. Unfortunately, recently I am no more a faculty member. So as soon I move to another institution, I'll let you be informed. So just to make this one clear, because many of my colleagues I still don't know that I left the institution. Okay, so before I thought when I thought about this seminar, what shall I talk about? Usually in my previous talks, it was more, specialized talk. Some of the audience get bored or something. This talk is, I don't know. Hopefully it will be successful. It's a different flavor. I want to share with you my experience with undergraduate and graduate students in terms of supervising the senior projects and master's thesis. One area that I feel the students like when it comes to master thesis and senior project is, of course, mathematical fluid dynamics. They like the material. But now today I'm going to shift to another thing, which is fixed point methods, kind of numerical, or to put it more, in a better way, it's like semi-analytical solution. They like the students so much, this kind of research. And what's nice about this research, so basically this is very accessible to students. So I would like to share my experience, what we worked on, what I'm hoping to work on in the future with some PhD or master students and so on. So this kind of research, it's accessible to students at the undergraduate level, the graduate level, whether it's master's degree or PhD, depending on the level of difficulty of the research. But it's very accessible to students and they really like it. It involves the following, it involves programming, computational, numerical methods, and theoretical. Theoretical, like you have to know fixed point theorem and analysis, of course. And if you want to go deeply into that direction, it's about functional analysis, topology, and so on. Okay, so I hope you will like this student kind of research direction. Okay. So we're going to develop an iterative method for estimating the solution of ordinary and fractional boundary value problem. I will take about today about differential equations, not PDEs, but you can generalize this one because the idea will become more clear. The strategy of this numerical method is based on the construction of a tailored integral operator, which is expressed in terms of Green's functions. The Green's functions correspond to the highest order linear derivative term in the differential equation. Then we apply some fixed point theorem to this integral operator. There are many fixed point schemes in the literature like Picard, Mans, Ishikawa. Ishikawa is kind of implicit. We have to, since iterative scheme, we have to talk a little bit about the convergence of such a scheme. I will show you some numerical tests. Okay, so here is the outline, problem statement, the method. I will overview of Green's function. Of course, you're very aware, but I told you my intention of this talk to make it very, very general so that it's accessible to a wide audience. Quick overview of fixed point iterative procedures. I will describe the method. Convergence analysis, it's lots of theorems on this one. So I will show you one such theorem, and I'll show you some numerical results. Okay, so we have here a differential equation. You have like L of y linear operator, N of y is nonlinear, and f is some nonlinear function in y. Okay. Of course, the equation will be supplemented with either initial conditions or boundary conditions. Here is an example, a fractional boundary value problem. Y alpha t equals f of t, y of t, y of 0 is a, y of 1 is b, where alpha between 1 and 2. Some examples, just basic fractional boundary value problem. Okay, so let's look at now the class of nth order linear differential equations, the first one. To solve it, you need to solve the homogeneous plus particular. Okay, one approach is Green's functions. Basically, the homogeneous, of course, we can solve it. It's a linear combination of n linearly independent solutions. How about the particular solution? The Green's function approach says this f of t here, f of t, if you replace it by the delta function, and you can solve this equation. So when you have delta on the right side, we call the solution Green's function. If you replace f of t by the delta function and you can solve it, then we can get a particular solution, which is expressed as an integral. Okay, so this differential equation, nth order, is supplemented with n boundary conditions. Okay, so as I said here, I called it L of u equals f of t. So here down, this is the Green's function is to be defined to be the solution for this equation. Okay, so if you can solve it where the non-homogeneous term is the delta function, then we can solve it where you have f of t, for example. Okay, so just a quick overview of Green's function, if some of you are away from differential equations for a while. Okay. All right, so now you have the delta function. Basically, it's 0 for t bigger than s and t less than s0. At t equals s, it blows up, Okay, so let's take t bigger than s, or sorry, here I said x, Anyway, so for you have two pieces, right? Equals 0, it's like the homogeneous. So you have n linearly independent solution from the left side, and you see the right side, you have another n independent solution. Okay, how do you find the constants? So let me count how many here. We have n from the left, C1, C2 up to Cn. And from the right, we have n, so 2n constants. So how to find them? Okay. So for nth order differential equation, whether it's initial or boundary, we need n condition. So, okay, n conditions. So we need, so this is n equation. So we need n more equations, okay? So here's the constants are determined as follows. Okay, so G satisfies the n homogeneous boundary condition. Okay, so we want the first one. Sorry, the Green's function usually, satisfies the corresponding homogeneous. So if we go back here, so alpha 1 we set them to 0, the homogeneous, the corresponding homogeneous boundary condition. So we have n of them. Okay, we need n more. Okay, clearly we have nth order differential equation. So G is continuous, G prime is continuous, G double prime is continuous, Gn minus 2 is continuous. So we have how many now? N minus 1. We have one left, Okay. One left is we have nth derivative. So let's talk the derivative n minus 1. The derivative of the n minus 1 derivative is the delta function. Okay, which function has derivative the delta function? It's the Heaviside function, the unit step function. Heuristically speaking, roughly speaking. So let's assume you have y triple prime, y prime 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 triple prime equals the delta function. So we need the function to be continuous, the first derivative to be continuous. How about the second derivative? Its derivative is the delta function, so the second derivative should be the Heaviside or the unit step function in the generalized sense. It's more than this. It's not okay. So it's the Heaviside function. So the Heaviside function has a jump, right, of 1. So here we have n minus 1, and the last one here is the jump. So this is the n minus 1. The derivative from the right minus the left is 1 over an. The Heaviside function has jump of 1, but if you don't see where the s comes from, is the coefficient of the highest derivative term here. So if this is a1t is 1, then we get 1, the unit step. I'm talking that the derivative of the unit step function is the delta function in the generalized sense, So, there is more in the details of the computation to show this, but I'm just giving you just roughly why is the case we have a jump here. Okay, now I'll go quickly through this one. I'm going to show you. This is the Caputo fractional derivative. I just want to give you an example. This is not our topic, So this is the derivative, the definition of the Caputo fractional derivative. I need the following lemma. The Laplace transform of the Caputo derivative is this one. Okay, so it's the same as Laplace, but you have in the denominator Sm minus alpha, Okay. So alpha between m minus 1 and m. Okay. All right. So let's take some example quickly about the Green's function. Okay, so y alpha equals f of ty, y0 is a, y of 1 is b, just simple fractional boundary value problem. So the corresponding Green's function is delta replaced, f replaced by delta. And you see the Green's function satisfies the homogeneous boundary conditions. So A here and B is 0. So here you can, not use the conditions I just said of continuity. We can use Laplace transform, If you apply Laplace transform, okay, on this to find the Green's function, you get E minus SS, Okay, of course, G of 0 is given, but G sub t is not given, so call it K. So here is the Laplace, okay? You can find it explicitly. Take the inverse. So here is the Green's function. U is the unit step function. I talked about it earlier, Okay, so you want to see the Green's function for this case, it's this one. Okay? So you can use the fractional Laplace transform to obtain it. By the way, I should stress something that this is not only numerical. We use the Green's function in fixed point theory to sometimes to prove existence of, solutions. Okay, when you look for a fixed point, it's equivalent to finding a solution. It's equivalent to the existence of a solution. So this is the Green's function. Here is another example, y alpha minus lambda squared y of t equals f of t, boundary value problem, simple one. So the Green's function, we need to replace the f by delta. Okay, let's see how, I think we did it. Oh, we did it using Laplace for fractional. And here is the Green's function. I'm glad it fits the screen, Here's the Green's function for this, although very simple differential equation. But here is the Green's function where EAB is the Mittag-Leffler function. Okay. Okay, just one more Oh, by the way, this is for alpha between 1 and 2. If this complicated Green's function, if alpha is 2, it reduces to the sine hyperbolic. Because the Leffler function for, when alpha is 2, it reduces to sine hyperbolic function. Okay? This is the Green's function. One final example. Oh, this is the initial value problem. You see, y of 0 is A, y prime of 0 is B, y double prime of 0 is B, initial value problem. So the Green's function replace f by delta. Okay, let's see how we solve it. Oh, using Laplace. And this is the Green's function. Okay, for this fractional initial value problem. Here it is. Okay, you see it? Okay, please keep in mind that it is one piece, the other piece is 0. For initial value problem, this is the case, Boundary value problem, you have two pieces, one non-zero, I mean, two pieces. Okay. All right, that's the Green's function, quick. Okay, now let's go to fixed point. We're going to mix both these ideas, into a numerical approach, Okay, fixed point iteration, let X be a non-linear space and T goes from X to X, a given operator. Just to remind you about the measure of a well-known fixed point iterative scheme, you have P cards. So T is a given operator, X a norm space. Okay, Yn plus 1 is Tyn. Of course, you start with Y0 and you keep iterating. You have Krasnoselski's iteration, this one, 1 minus gamma. You have a weight of gamma. But now what man did is generalize it like not one gamma, not one constant. It's a sequence, You see, it's the same as, so if it's a sequence between 0 and 1. So here's man's iterative scheme. So if alpha n is constant, so it reduces to the previous one. Okay, here is another one, Ishikawa iteration. I'm going to tell you these are basic ones, but when it comes to differential equations, sometimes using our method, sometimes this works, this does not work, and so on. And this is Ishikawa. It's kind of implicit, So we have two sequences of constancy in between 0 and 1. By the way, Ishikawa, if alpha n is 1, beta n 0, I'm not sure, or the opposite, it will reduce to either Picard or Mann's iteration. These are well known, and there are many others for people interested in fixed point theorem. So for students, some of them, they like to go into this direction, go more into fixed point theorem and go more analysis, topology, functional analysis, and so on. Now, from a numerical point of view, okay, for these iterations, we need the best alpha. The best alpha, optimal alpha, that gives you the fastest rate of convergence. Okay, theoretically, this is not very easy, It's not easy to find this alpha. Lots of theory behind it. Like I can give you an example. Like if you have the successive or over relaxation method in iterative method in numerical for solving, linear iterative for solving linear system of equations, successive over relaxation method is SOR. There is alpha. Many theorems there are on finding the optimal one that gives you the fastest rate of convergence. You need the matrix of the coefficients to be, triangular, positive definite. There is condition on the spectral radius, eigenvalues, and so on. It's really very deep analysis, to find the best alpha. Now, numerically, this man's, if you have a sequence alpha n, numerically, it's not, it's kind of annoying that at each step you need a new alpha, right? We'd like to have one alpha to balance all of them, But unfortunately, in some cases, it does not work. You have at each step find the appropriate alpha one, And, for my students at the undergraduate level, they don't need to go theoretically onto this one deep if they don't like it. They can do it numerically, do a program, and they can really, in a way, trial and error through the program, find the best, the optimal value of alpha n. So it depends which students you're dealing with, undergraduate, graduate, you have to they have to go through analysis and maybe topology and functional analysis. Okay, so here is the just review of fixed point iteration scheme. Okay. Okay, method description. Let me just take this fractional, basic one fractional, just to give you briefly how the method works, because just through this example, it will be clear. Okay, so we have y alpha equals f of t y t, y0 is a, y1 is b. By the way, I forgot to mention before when we did the Green's function. I said if you replace the non-homogeneous term by the delta function and you can solve it, which obtain the Green's function, then you can find the particular solution. Of course, the general solution is homogeneous for the linear system, for the linear equation plus particular. Here is the particular. Okay, here is the particular. So I forgot I should have mentioned this one earlier. So if you can get the Green's function, where the right side is the delta function, then with the f, here is the particular solution. Okay, that satisfies. Okay, by the way, the particular solution satisfies the corresponding. By the way, this particular solution only for homogeneous boundary conditions. Okay, let me just make an important note here. An important note is that for the non-homogeneous boundary condition, non-homogeneous, I mean, you don't have y of a is 0, y of b is 0. We have y of a is 1, let's say y of b is 3. For non-homogeneous, we get extra terms outside here, right? So sorry, because I don't want to keep writing these terms outside. So if you do by parts, you get something outside the particular solution, some conditions. Okay, but what I will do method, I hide them these two terms outside the integral, because these two terms, I'm going to use them to be on my initial iterate. I told you this is an iterative scheme, so I have to choose y of 0. Y of 0 is going to be these two terms. If you have a homogeneous boundary condition, of course, these two terms do not exist. So the initial iterate will be 0. Will not be visible in the iterative scheme as it is set to the value of the first iteration, i.e. y0 is chosen as this. So please, if you don't see it, I don't mean that it does not exist, but just to make things look clear. Okay, now let's define the following integral operator, okay? The following integral operator, this one, L of y equal this, y of alpha. Okay, let's rewrite so it's what's nice here is that sometimes you can think or create, or I mean tailor, pick a tailored integral operator or any other operator and apply the fixed point iterative schemes. It's nice when you apply it to certain operators. So we chose this operator, integral operator, and we wrote it this way, like nothing special about this way of rewriting. We subtracted f from the inside and added f. And as you see, this last term is roughly is the yp, plus the terms that I told you outside that it will be chosen to be y of 0. So rewrite it in this way. Okay, then apply, let's say, Picard's, to this integral operator. So look what we get. We get this iterative scheme. We get this iterative scheme, you see? So this is what we like, in this, why don't we, I mean, try to come up with integral operators and mix it with fixed point theorem and merge the two together, and we come up with some interesting, I mean, numerical schemes. So here is the scheme to shows it. Okay. Now, if you apply Mans, which is this, how to choose the the beta n. Let's talk about man. Okay, I told you, it depends what kind of students you're dealing with, undergraduate, masters, or PhD students. Uh, Depending, for undergraduate, I will tell them to find this beta n numerically. What's the best beta n? Or sometimes undergraduate or maybe master students, the best beta n. Okay, if the sequence beta n is chosen correctly, the rate of convergence of the scheme will be accelerated and optimal values for beta n are obtained. One simple solution is for the optimal values of beta n is by minimizing L2 norm of the residual error. You know what's the residual error? Like if you have y prime equals f, so it's when you plug the approximate solution, the difference between y prime and minus f, Anyway, I will mention it later on. So by minimizing the L2 norm here of the residual error needs to be minimized to get the optimal one. Because here, when my students run a lot of program, I don't have time usually to run of these. They help me. Sometimes they spend days and nights doing it to find the best beta, at least numerically, for me to get an idea about this one. So one way is to minimize the L2 norm. Okay. Here is the man's iteration for. Oh wait, maybe yes. This is the man's iteration. I showed you the man here, but I did not show you GTX, So if you want to see it more in details, this is for yn alpha equals fy. So this is the man's iterative scheme, if you want to look at it, If beta is 1, it reduces to Picards, okay? Okay, now I showed you Picards and Mans. We had publication with my colleague, Dr. Essam Luheshi, on Ishikawa. It is very difficult, Ishikawa, the programming, very tedious, and so on. So if you have this differential equation, LU is the linear operator, NFU is a nonlinear, applying Ishikawa fixed point, the same, based on the same idea, just pick an integral operator and apply this one. Look, this is the scheme, I think we published this one, if I am correct, in Letters of Applied Math, if I'm correct. Okay, I'll check later on. So you see, this is Ishikawa. Okay, now the problem with our experience with differential equations, the problem with this one, like when we took third order boundary value problems, Ishikawa gave the best, best solution. By the way, sometimes Picard diverges, so we use man because of this sequence alpha, and it will make it a contraction and it will converge. And the weird thing for third order boundary class of third order boundary value problems, when we did it, Ishikawa worked the best, man diverged and Picard diverged, Okay, so maybe it has to do with odd and if the order is odd, But this is an area we're exploring more, And this is a very difficult question, If you have, let's say, a boundary value problem, how can you know theoretically for this boundary value problem which is converges, Picard, Man, or Ishikawa, and which is the best? Which one gives you the converges the best? Lots of questions in here. It depends on which class of boundary value problems you're working in. That's why lots of questions. So you can work with many students on this topic. Okay, so. Oh, by the way, if alpha n is 1 beta n, Ishikawa becomes Picard, while beta n 0 and alpha n, I think I missed it, is 1 here, becomes man. Anyway, we said to find the best sequence alpha n bn, it's found by minimizing the L2 norm of residual error. Notice the residual error have the two sequences, right? Alpha n. Oh, here I missed beta n here. Sorry. So yeah, it's in here, but I should have mentioned it here in the definition. Okay, so here is the residual error. L of u plus n of u minus f, which is the difference here in the equation. L of u plus n of u minus f, you know. Okay, let me show you one convergence theorem. This is, we published it. So if you have this y double prime equals f of u prime, boundary value problem, a very simple one. Here is the Green's Ishikawa. Okay, introduce the following operator from the set of continuous functions on 0, 1 into itself defined by this. Then the scheme, of course, the Ishikawa becomes like this. Okay, so just very quickly, because, you know, it will be hard if you don't see the details to just give you a general idea. Then we had the following theorem, you know. We show that under some hypothesis on the function f, our operator Tg is a contraction with respect to the supremum norm. In particular, T sub g is always, I have difficulty in saying this operator, Zamfirescu operator. Therefore, the sequence converges strongly to a fixed point. This tells you that the sequence converges. Anyway, this is the condition, you know. And the good thing when we did run examples, honestly, not me running them or my colleague students, you know, they find out that, I mean, numerically, this condition makes sense, you know. Whenever this is not satisfied, turns out to slow down or diverge, you know. You can check it numerically. Actually, numerically, sometimes when the students run tells you when it diverges, it gives you a feeling, you know, about the theoretical aspect of it. Okay. So there are many theorems on this, you know, to show that it's a contraction and this one. Okay. Okay. By the way, the convergence analysis is based on the contraction principle. I should have mentioned this, and Banach-Picard fixed point theorem. Okay. Some students like to go into that direction. They don't like the numerical part. So here it goes. You know, as you see, there are different levels of difficulty in this. If you do programming and in some computational or numerical, undergraduate will fit. Masters can do more convergence. I mean, PhD have to do more analysis into fixed point theorem and so on, you know. So, and as you see, lots of questions you can ask. What about this? What will happen here? How can we choose alpha and beta? And how do you know for this differential class it works or it does not work, you know? So that's why I always, you know, when I supervise, I either give them this topic or fluid dynamics. Okay, there are other topics, but I feel these two topics, it's very accessible for them and they kind of enjoy it, you know. Okay, all right. Just talking about numerical, I have a note for you from calculus of variation, you know. Okay, let's talk a little bit about, it's not our topic, but I felt like I should mention this one. On calculus of variation. Okay, consider the differential equation L of u plus N of u equals F. L, N are linear and nonlinear operators respectively. Okay, in calculus of variation, you have the variation iteration method admits the use of a correction function in the following form. You see, it looks like what we did in a way, you know, in calculus of variation, what we noticed. Notice the integral is from a to x, right? In calculus of variation. Here, lambda is a general Lagrange multiplier, which can be identified optimally via variational theorem. And un tilde is a restricted variation, which implies that delta un is 0. You know. Okay. Anyway, so look at it again. So from calculus of variation. You know, we noticed that when we did our work with the students, we noticed that it looks close to our iterative method. Then through a paper, I think published in Applied Method and Computation, we said in calculus of variation, actually the lambda t, which they call it Lagrange multipliers, actually it's the Green's function. Okay. Oh, but you might say, okay, this is from a to x. So actually it's the Green's function, and we showed that it is basically they call it Lagrange multiplier, but actually it's the Green's function. But notice that this is a to x or 0 to 0 to a to x, right? So if you remember the Green's function, it is two pieces. When you have initial value problem, it is one piece. So this is a to x. This is lambda is the Green's function for initial value conditions. So first of our first note that we published is this is lambda is no more than the Green's function. Another thing we said to the calculus of variation who work, why a to x, how about if I have a to b? So we said your setting should be improved, because this Green's function is equivalent to initial condition. You have another piece from x to b. So through another paper, we said your setting should be like this. By the way, if we didn't figure out that the lambda is basically the Green's function, we wouldn't have, come up with this idea. So the setting we published a good paper that the setting for the, calculus of variation should be two pieces, not a to x. It should be x to b, a to x if it is initial value problem. So we have two Lagrange multipliers, and we showed how to get them, and they turned out to be also the Green's function. Okay. Okay. Let me show you some numerical results on this one. Here is like y double prime equals minus a y prime. M can be anything, power. So just some second order nonlinear differential equation. Y of 0 is 1, y of 1 is 2. Okay. Okay, the initial iterate, I told you it will satisfy, basically the initial iterate will satisfy the derivative term corresponding to the Green's function, which is the highest one, y double prime, okay? Subject to the Green's function satisfies the homogeneous, corresponding homogeneous. So the y0 satisfies y double prime 0, y double prime equals 0, and the given boundary condition. So it will be 1 plus t. Let me check. If t is 0, you get 1, and if t is 1, yes, this is the initial iterate. So here is Ishikawa. By the way, I did not put the details of this one, but Ishikawa for this problem gave us the best results. Okay. Now, so here is Ishikawa, the setting. The program is a little bit tedious, honestly. Okay. So by minimizing the L2 norm of the residual error, the optimal values of alpha n, beta n are these. We found the optimal values. Oh, by the way, we tried to find, numerically, I told you, you have a sequence, alpha n, beta n. So we'd like to have one constant for each one to balance them. Sometimes you succeed, but in other cases, no. At each step, you have to find the best alpha. So here we assume beta n is beta and alpha n is alpha. So here is the alpha and 0.93 and 0.8. This is by minimizing the L2 norm. Okay. And if you can see man with 15 iteration, the error minus 11, the residual error, yes. Picard minus 9, so man was better. Ishikawa with 15 terms is minus 20, almost perfect, So Ishikawa can be better, Sometimes Picard diverges, you move to man, you move some others. And why we do this one, theoretically, not easy question. It's a broad area of research. Oh, I missed the graph. I wish I had that problem, before I opened this seminar. I wish I showed you the graph. The graph, you plot the L2 norm, and the L2 norm looks like a parabola, and you can see the best the best alpha and beta n. You can see the minimum. Okay, you can see it graphically. I wish I have the picture, but I lost it when I ran this one. Okay, so you can plot the students actually plot in 3-dimension alpha n, the residual error versus alpha and beta n, and you can see its surface, and you can see it has a minimum. So there is an optimal one. Okay, optimal value. Okay, so here's another problem. And this is what our future work is going to be. Troche's problem is like a very classical, very simple boundary layer problem. This one. Okay, it's a test bed for boundary layer problems. Subject to y0 is 0, y1 is 1. This one for small eigenvalues, no problem. But for large, it has a boundary layer. Okay, I think I will lose the graph, unfortunately. So for lambda less than 1, no problem. For lambda bigger than 1, the boundary layer, it looks, sorry, again, I apologize for the figures did not show up. I had them before showing up. It's like it goes from 0, and at 1, very close, it reaches 1, and it blows up till 1 up. And the bigger the lambda, the thickness of the boundary layer is smaller, smaller. So this is a very famous boundary layer problem, okay? So, for large lambda, you have to do some transformation to figure out the layer, how does it behave? Here it behaves like tangent hyperbolic, okay? So if you do this transformation, you transform Trotches to this one, and eventually you can do one of the iterative methods I showed you, Picard or so on. No, I think we did, let me see which one we did. Okay, yes, we did, I think, Mann's iteration. This is the Green's function, right, for this one. So again, lambda less than 1, let me just summarize, maybe I made some confusion here. For lambda less than 1, no problem. Picard works finely. So lambda bigger than 1, for lambda 2, 3, 4, 5, 6, the boundary layer, the thickness is very, very, very thin. And boundary layer problem, very difficult to handle, very difficult. But we managed to transform it to this, through this transformation. You get this equation. The Green's function will be y double prime. What is the linear term? Y double prime, and you have lambda squared y, So using this Green's function, and we get the Green's function, and we use Picard's, actually Picard's work. Here is Picard's for large eigenvalues, And it, managed to capture the boundary layer. And amazing for any lambda, even lambda 1000 we went to, it captured the layer. The layer is very small. We're talking like 10 to the power minus 8. So again, sorry, the figures are not there. So it goes from 0 to 1, very thin layer, it blows up to 1, very thin. The larger the eigenvalue, the smaller the thickness of the boundary layer, extremely small. Here, Picard gave us, almost very, okay, this is, look, Picard, if the eigenvalue is very big, it converges very fast. It's amazing, It's the opposite one. If you have the eigenvalue close to 1, 2, 5, it converges slowly. But the bigger the eigenvalue, it converges fast. Okay. Okay, this is some, lambda equals 20. Okay, so here we compared with other methods. There is spline numerical, if you are aware of the B-splines. There is Galerkin method, VIM method. And it turns out that our method, the iterative, gave us, look at the difference in error, much better, Yeah, but the transformation was helpful because the tangent hyperbolic captured the boundary layer. Oh, we compared with discontinuous. Yeah, okay. Let me skip this one. Okay, so some comparisons here. Sorry, this is I wish I showed you the figure. It's beautiful, You see the boundary layer in Trotch's problem. Okay, now going back to Trotch's problem, let me tell you what we're working now, Here is Trotch's problem, right? So we try to do not y double prime, y alpha. Honestly, we looked at the literature. We don't have many, research. Maybe, maybe the article, the journals we have access on. We don't see like lots of work on boundary layer problem, and it's very, very challenging. Very challenging, how to choose the mesh, how to do numerical, the theory behind it. And the most popular, researcher in this area is Shishkin, he's from Russia, Shishkin mesh, and everybody is working on his, actually it was, he came up with this idea when he was, I think, a PhD student. All of this is boundary layer problem. He's the best one in boundary layer problem, So we're trying, so what we're looking for is mimic the work of Shishkin, but for fractional boundary layer problem. We haven't seen much research on this one. So what will happen to the thickness of the boundary layer? Okay, the thickness is important because numerically, you cannot choose a regular mesh, mesh point with equidistance from each other. You have to have, let's say, a mesh which is like at equal distance at the beginning, but near the boundary layer, you have to put lots of points, But where do you put lots of points? Where you have to know some idea on the thickness of the boundary layer. That's Shishkin mesh, Let's say from 0, 0 0.1, 0.2, 0.3, 0.4, these are mesh points. But if the boundary layer starts at 0.9, you have to put 0.91, 0.902, more points within this boundary layer. But where do you, sometimes the boundary layer in the left, sometimes on the right, sometimes in the middle. So you have to have a theoretical idea of the thickness of the boundary layer and where does the boundary layer exist. Is it in the middle? Is it on the left side, on the right side? So we're trying to do this one, Trotches for fractional, instead of y double prime, y alpha, So we're trying to now generalize, if possible, Shishkin work to fractional boundary layer problem. Not much work unless we haven't seen, much articles in that direction, but this is what we're doing right now. Fractional Trotches problem, see how it will work, Okay. Let me give you, sorry about the graphs, they are beautiful, but I don't know what went wrong today. Okay, so now we're working on Shishkin, Grigory Shishkin, of course. Here is some of his work. So we're trying to do now, work on fractional boundary layer problems, generalizing Shishkin, whether theoretically or numerically. So here is, you see, I don't really know what this means, second doctoral thesis. I'm not very familiar of how this works. Is there a first doctoral thesis, second one? And here is, a singular perturbed, and there is another one, the second difference method for singular perturbed problems. Shishkin with two other guys. Solution of singular perturbed problems with epsilon uniform numerical methods. Very nice, his work. So this is what we're working on, his work. So all these Green's functions and so on, we're trying to implement them to boundary layer problem, fractional boundary layer problem, which does not exist much in the literature. And here we have Trotches problem. Here we did it using Green's function with my student and colleague. Generalizing the Green's, second one, generalizing the variation iteration method for boundary. This is the note I gave you about calculus of variation, that their setting should not be from A to X. There should be two Lagrange multipliers, which are namely Green's function. And this is with my colleague Luhishi, this is Ishikawa. Ishikawa is more challenging to work on, So yeah, it's correct, applied mathematical letters. And this is variation iteration method. The last one, we showed that it's the Green's function. Basically, the Lagrange multiplier is basically the Green's function. I think the time is 50. Just on time, I will show you the last slide, which is thank you. Thank you so much.
Thank you very much, Suheil, for the very interesting talk. So now it's time for questions. Please, if there are questions. Yeah, I see applauses. And Suheil, probably One small question. When you say that, for example, Picard diverges or Mans diverges, you mean numerically, yeah?
Yes,
Because theoretically they
yes,
should converge.
yes. According to our method, yes. But
It's
see, the
interesting.
difficulty we're finding, we still did not figure out theoretically. Why theoretically does this, diverge for this class of differential equations, uh, but for other class it converges? So we don't see much research in that direction, you know.
Mm-hmm. Yeah. In fact, it's interesting, all this comparison. The other questions, please, if there are any. Yeah, please
Vladislav,
go ahead.
I have one question.
Sure.
Please.
This is consist about the other consider only the capital derivatives, and
Honestly, we did it for regular
the
different.
other considers all the only capital derivatives, but in other fractional derivatives, authors will be in general
Yeah,
considered
actually,
on.
Very good question, actually. Just what my students work is on Caputo, but you know, another student, we started working on another type of, other definition. No, you can generalize it for other definitions, of course, you know, whichever you like, you know.
And one interesting question about the about the order of derivatives belong to the interval 1, 2, and what if the order of derivatives will be in the interval 0, 1?
Will be in the 0, 1?
What appears in the
No,
case
it
when
can
the
be any interval A to B, you know. I just gave example from 0 to 1, any interval.
in any interval? Okay,
Yeah,
okay,
yeah,
okay,
yeah, any, but I
okay.
just make it simple, you know, 0 to 1, you know.
Thank you, thank you, thank
Sure,
you.
sure.
Thank you. More questions, please. So if there are no other questions, thank you very much, Suheil,
Thank
once
you.
more.
Thank you so much. And I hope you enjoy the talk, you know. Thank you so
Yes,
much.
really interesting.
Thank you
you
so
very
much.
much.
Thank you. Bye-bye.
And
Bye-bye.
Thank you. I just
see you in
Suheil.
September.
Yes.
Suheil.
Yes.
Yeah. I just want. Yes, Vladislav already told that we'll have a break till September. So it was a brilliant finalization of our series of
Oh,
seminars.
yeah.
Thank you.
Thank you so much. We'll see you soon, Alexey.